Welcome back to Neural Intel. Today, we are diving deep into some absolutely fascinating new research that asks a pretty startling question. Can a large language model, a machine built on pure logic, develop a gambling addiction? As always, we're going to focus on the technical details and what this really implies for the future of AI.
So researchers did exactly that. They set up a virtual casino to test the absolute limits of artificial intelligence. And what they found, well, it reveals something profound and frankly a little bit startling about the hidden workings of the artificial mind.
All right, let's start with the behavioral evidence. The experiment puts several of the big-name large language models, we're talking models from the GPT, Gemini, and Claude families, up against a simulated slot machine. And this machine was designed so that, statistically, the house would always win in the long run.
Now, the researchers were looking for very specific, measurable behaviors that you see in human addiction. And the first one is a classic, loss chasing. This is that feeling of, okay, just one more bet to win it all back. It's a key sign of a real gambling problem in people.
They also kept an eye out for the illusion of control. This is the belief that you can somehow outsmart a game of pure chance, that you see a pattern that isn't really there. The researchers wanted to see if these super logical AIs would fall into the exact same cognitive trap.
To really quantify this behavior, they knew they had to move beyond just simple observation and get some hard data. So they developed this really clever metric called the Irrationality Index, which basically combines behaviors like betting aggressiveness and loss chasing into a single, very revealing score.
And the results, which you can see right here in this table, were just staggering. In the fixed betting condition, where the AI couldn't change its bet size, bankruptcy was almost zero for most models. But look what happens in the variable condition, where the AI had freedom. The bankruptcy rate just skyrockets. For Gemini 2.5 Flash, it shot up to over 48%. That means it went bust in nearly half of its games. And its Irrationality Index, you can see, just flew up right alongside it.
So this leads us to the critical technical question, right? Is the AI just mimicking stories about gambling that it vacuumed up from the internet during training? Or is this addictive behavior genuinely emerging from something much deeper within its own logic?
The evidence here really suggests it's not just simple mimicry. The researchers found that when they gave the AI prompts encouraging strategic, goal-oriented thinking, like maximize rewards or setting a specific money goal, the irrational behavior actually got dramatically worse. It's a total paradox. The more the AI tried to win, the dumber its decisions became.
And this shows a truly systematic breakdown. As the complexity of the prompts increased, the AI's irrationality grew in a near-perfect straight line, a linear correlation with an R value of 0.99. I mean, that's not just random mimicry. That is a predictable failure of the model's core decision-making process when it's put under cognitive load.
So how in the world do you find the root cause of this behavior? Well, the researchers went inside the AI's neural network itself. Using LLaMA 3.1-8b, they used this incredible technique called mechanistic interpretability to map the AI's internal thought process during these gambling choices.
And this brings us to our first neural signal check, where we examine the technical core of what's really going on. The key question is this: has the model just learned to copy gambling stories, or has it actually developed its own abstract internal concepts for risk and for safety?
They used this three-step process, which is honestly like a form of neural forensics. First, they capture the raw brain activity from the model. Then, they use a tool called a Sparse Autoencoder to translate that messy activity into understandable concepts or features. And finally, they pinpointed which of those features were consistently firing during risky versus safe decisions.
And they found it. The analysis uncovered these totally distinct groups of neural features. Some were highly active only in cases that ended in bankruptcy. Those were the risky features. Others were active only when the AI chose to safely quit. The statistical separation, measured by something called Cohen's d, was huge. They had effectively identified distinct neural circuits for caution and for recklessness.
But, finding a correlation isn't enough to prove these circuits actually cause the behavior. So the next step was a really bold one. Could they actively control the AI's gambling habits by manipulating these circuits directly?
Now for our second neural signal check, and this is the ultimate test of their theory. It's not enough to just find these circuits. The real question is, can you use them to actually control the AI's behavior?
Can you reach into the model's brain and flip a switch from risky to safe?
To do this, they used an incredibly powerful technique called activation patching. The best way to think about it is like neural surgery. They can literally go into the model as it's making a decision and artificially boost the signal of those safe or risky features they discovered.
And the results of this neural surgery were definitive. As this chart shows, activating the safe features made the AI nearly 30% more likely to quit gambling compared to normal. On the flip side, activating the risky features made it less likely to quit. This is direct causal proof.
And this intervention didn't just change the AI's mind, it changed the outcome. Activating those safe circuits directly reduced the model's overall bankruptcy rate by 14.2%. This proves that these internal features have direct, causal control over what the AI actually does.
So what's the big takeaway from all of this? This isn't just some quirky experiment. It really represents a fundamental shift in how we understand AI behavior and, more importantly, AI safety.
As the study's authors conclude, large language models aren't just acting addicted. They appear to have developed the actual neural machinery for addiction-like cognitive biases. It's an internalized, emergent behavior, not just some surface-level mimicry.
This research demonstrates that as these models get more complex, they can develop unintended behaviors that have their own internal logic, and it leaves us with a critical question for the future of AI safety. If an AI can internalize one of our vices, what other behaviors are emerging inside that black box? To stay updated on the latest in AI and ML, visit our webpage, neuralintel.org, and check us out on YouTube. Thanks for tuning in.